During this presentation, we have to talk about Sackur Tetrode equation. For that, we should write the relation between entropy and thermodynamical probability. Here, S is our entropy, K, Boltzmann constant, W is a thermodynamical probability, that is the possible microstates for the given macro state. This is our W. According to Maxwell-Boltzmann statistics, according to MB statistics, the thermodynamical probability W is given by this relation. See here, capital N represents total number of molecules. Gi is our state of degeneracy, that is the number of microstates in a particular energy level. Ni represents the number of particles occupying a particular state. So this is equation 1, this is equation 2. In equation 1, ln W is present. Therefore, we have to take ln for this equation 2. Ln W is equal to ln n factorial plus summation over I Ni ln Gi minus summation over I ln Ni factorial. So this is equation 3. These two factors are in product, so we have to add these two. This is in division, so we have to subtract. So you take ln. According to Stirling approximation, ln Ni factorial is equal to Ni ln Ni minus Ni. This is the meaning for ln Ni factorial. Now we have to use this in equation 3. Ln W, which is equal to ln n factorial plus summation over Ni ln Gi minus ln Ni factorial. We have to use this summation over I Ni ln Ni, then minus and minus plus summation over I Ni. So this is equation number 4. From the right hand side of equation 4, we have to take out this Ni as a common term. This is equal to ln n factorial summation over I Ni ln Gi minus ln Ni plus 1. This is equation 5. Just we have taken out this one as a common term. See this is in log A minus log B, which is log ABB. This is equal to ln n factorial summation over I Ni ln Gi by Ni plus 1. This is equation number 6. This is our ln W. Now we have to go further. For that, we should consider our MB distribution. Number of particles occupying a particular state is given by the formula Ni equal to summation of I Gi e power minus of alpha plus beta into Ei. We have to use that relation. See here, according to MB distribution, number of particles occupying a particular state equal to Gi e power minus alpha plus beta into A. This is the formula for Ni. From this, Ni by Gi equal to e power minus alpha plus beta A. Then Gi by Ni equal to e power alpha plus beta A. This negative sign is changed into positive. If you change Ni by J into J by Ni. But we need the value of ln Gi by Ni. Then ln Gi by Ni equal to, if you take ln, the D goes out. Alpha plus beta A. This is the value of ln Gi by Ni. Now we have to substitute the value of ln Gi by Ni in equation 6. Ln W, which is equal to ln n factorial summation over I Ni. Then instead of ln Gi by Ni, we have to substitute alpha plus beta A. Then write on this one as such. So this is equation number 7. Then this is modified as ln n factorial alpha into summation over I Ni plus beta summation over I Ni Ei plus summation over I Ni. Say this is equation 8. Now we should substitute the values. You know the value of summation over I Ni. Summation over I Ni is our capital N, total number of molecules. This is ln n factorial plus alpha into capital N plus beta into Ni Ei is our E, total energy of the particle. E summation over I Ni equal to N Ni Ei equal to total energy E plus N. So this is equation number 9. Now we have to substitute the values of alpha, beta and E. Alpha is minus ln n by b h square divided by 2 pi m kt power 3 by 2. This is alpha. This is value of alpha. Then the value of beta is 1 by kt. Then E equal to 3 by 2 n kt. We know that energy associated with each degrees of freedom is half kt for a single molecule. Here the 3 degrees of freedom is 3. Energy associated with each degrees of freedom is half kt. X, Y, Z are the 3 coordinates. So the degrees of freedom is 3. So 3 by 2 kt is the energy associated with the single molecule. But the system contains n number of molecules. Therefore the total energy E equal to 3 by 2 n kt. Now we have to substitute all these values in equation 9. See, ln W equal to ln n factorial minus n ln n by b h square divided by 2 pi m kt. This is our Boltzmann constant. Entire power 3 by 2. Then beta 1 by kt e equal to 3 by 2 n kt plus this n. Now you have to simplify this. This is equal to ln n factorial plus n into ln n by b. We have changed this negation into positive, therefore this term is modified in this form. 2 pi m kt by h square power 3 by 2 plus kt cancelled out. 3 by 2 n plus n is 5 by 2 n. This is our equation 10. Now we should reach our Tetrode equation. S equal to k ln W, the relation connecting entropy and thermodynamical property. S equal to, this is ln W. Equation 10 provides the value of ln W. Now we have to write k ln W. Take this term first, 5 by 2 n k. Then take this term n k ln n by b 2 pi m kt divided by h square power 3 by 2 plus k ln n factorial. This is our Sackur Tetrode equation. Now you have to give the physical significance of this equation. 5 by 2 nk plus nk ln n by v 2 pi m kt by h square power 3 by 2 plus k ln n factorial is our Tetrode equation. Now you have to give the physical significance of this equation. Write down this equation at the top. S equal to 5 by 2 nk plus nk ln n by v 2 pi m kt by h square power 3 by 2 plus k ln n factorial. So this is equation 11. Now I have to give the physical significance of this equation the following way. Consider the compartments A and B filled with two different gases at different volumes and isolated from each other with the help of a separator. Say this is the separator. Let S1 be the entropy of the gas in A and S2 be the entropy of the gas in B. Once the separator is removed, the molecules are allowed to mix. If you concentrate the entropy of the mixed state, it should be increased. On mixing two different gases, the entropy of the mixed state should increase. This is a rule. Because mixing of two different gases is an irreversible process. Mixing of two different gases is an irreversible process. Here, different gases means these gases are distinguishable. On mixing two different gases, the entropy of the mixed state should increase. This is a general rule. Because mixing of two different gases is an irreversible process. According to Clausius, the change in entropy in an irreversible process is greater than 0. That is ds greater than 0. According to Clausius, the change in entropy in an irreversible process is greater than 0. ds means change in entropy. Therefore, S mixed, entropy of the mixed state should be greater than S1 plus S2. See here, the entropy of the mixed state should be greater than sum of the entropies before mixing. S1 be the entropy of the gas in A, S2 be the entropy of the gas in B. According to Clausius, the change in entropy in an irreversible process is greater than 0. Then Ts, that is change in entropy, should be greater than 0, which means that entropy of the mixed state is greater than sum of the entropies before mixing. Sum of the entropies before mixing. If you use this Tetrode equation also gives the same result. There is no problem in this case. That means mixing of two different gases is an irreversible process. The entropy of the mixed state should be greater than the sum of the entropies before mixing. This is a general rule. That rule is satisfied by the Sackur Tetrode equation. Now we may go to the second case. Suppose the two compartments are mixed with the ideal gases. That means identical gases. Not ideal, identical. Identical means both of them are either hydrogen or nitrogen. A is filled with hydrogen, B is also filled with hydrogen. Now we may write on mixing the identical, that means indistinguishable, on mixing identical gases, the entropy of the mixed state or we may write some other way, the change in entropy on mixing the identical gases, the change in entropy should be 0. See here, on mixing the identical gases, suppose A and B are filled with the same gases, hydrogen and hydrogen or nitrogen and nitrogen. On mixing the identical gases, the change in entropy should be 0, which means that Ds equal to 0, then S equal to constant, which means that S mixed, entropy of the mixed state should equal sum of the entropies before mixing. This is our expectation. According to quantum statistics, if we mix two identical gases, this is hydrogen, this is also hydrogen. Identical particles are indistinguishable because their particle coordinate may overlap. If you mix the identical gases, the change in entropy should be 0 because the reason you have to write mixing of identical gases is a reversible process. In a reversible process, the change in entropy is 0. Therefore, S mixed equal to S1 plus S2. That means entropy before mixing. Change in entropy equal to 0 means entropy is a constant. This is the conclusion we have arrived with the help of our quantum statistics. Now we will come to our Tetrode equation. If you apply the Tetrode equation to this case, that means if both the compartments are filled with the same gas, Tetrode equation shows that the entropy of the mixed state is greater than that of the entropy of the gases before mixing. That is paradox. I have to write. This is our quantum statistics result. If you apply our Tetrode equation, however, our Tetrode equation contradicts with our quantum statistics. On the basis of Tetrode equation, during the mixing process, two identical gases, the mixed state entropy shows an increased value, which is a paradox. On the basis of quantum statistics, if you mix two identical gases, the mixed state entropy should equal the sum of the entropies before mixing. But if you apply our Sackur Tetrode equation, the mixed state entropy increases. The reason is, I'm going to write the reason. According to classical mechanics, all the particles are distinguishable. And hence the Tetrode equation treats the system as an irreversible one. In an irreversible process, the entropy of the mixed state should be greater than the sum of the entropies before mixing. This is a paradox. Identical particles are indistinguishable. That is the conclusion we arrived from our quantum statistics. But the Tetrode equation corresponds to classical statistics. According to classical mechanics, all the particles are distinguishable. Actually, identical particles are indistinguishable. But this Tetrode equation treats that all the particles are distinguishable. If the particles are distinguishable, it comes under irreversible process. In an irreversible process, the change in entropy is greater than 0, which means that the entropy of the mixed state is greater than the sum of the entropies before mixing. This is a paradox. To resolve this paradox, we have to discard the last term present in the equation 11. To remove the paradox, we have to discard the last term. This term should be discarded. If you discard this term, the paradox existing with our Sackur Tetrode equation is removed, because while arranging particles, so A and B are two particles which are arranged in states 1 and 2. If it is distinguishable, we can get two different states. Suppose A is occupying the first state and B is occupying a second state, we can represent one state. Suppose the particles A and B are interchanged, we can get another one state. The entropy also contributing in this way. Therefore, there is some meaning in adding n factorial term in the classical aspect. But according to quantum statistics, the particles A and B are occupying the states 1 and 2, even though if you interchange the particles, that means A is shifted to the state 2 and B is shifted to state 1, there is no meaning. We won't get a new state. In this way, while treating this equation for mixing of two identical gases, the last term k log n factorial should be discarded. If you discard the term, the paradox existing with the Sackur Tetrode equation is removed. That's all about our Gibbs paradox, and we explained the paradox and the removal of paradox with the help of our Sackur Tetrode equation. Thank you.